So we're having a review session, and that will be on practice test 2. So if you guys want to pull that up, it's on the course website, and I think I attached it on the classroom too. Yes, I did. The answer key is also on the course website, but we'll go over the answers too here. Only thing is the key doesn't have explanations, so that's why I find this session helpful. Yes, I'm going to record this. It's recording right now, and I'll post it on YouTube as like a private link or like unlisted, and then link it in the classroom. And I'll do that tonight as soon as I can. Okay, we'll get started then. Let me know if you guys have any questions. And okay, cool. So we have a bunch of true and false and multiple choice, which I don't really like in math, but that's what your exam is going to be, I think. So we'll get used to them. Okay, so number 1, if the second derivative is greater than 0, so if the second derivative is positive over the interval 2, 3, then f of x is increasing over 2, 3. Okay, so what does the second derivative tell us? It tells us concavity, right? We know that the first derivative tells us velocity, so instantaneous rate of change. Is it increasing or decreasing? And the second derivative tells us concavity. Is it concave up or concave down? So for this question, if the second derivative is positive, all it's telling us is that the original function, f of x, is concave up over 2, 3. So it does not mean that f of x is increasing over 2, 3. It's possible that it could be decreasing but concave up. So it could be like, how would it be like? Okay, I'm not going to try to draw it because maybe I don't have the brain power right now. But just remember that just because the second derivative is positive, that doesn't mean the first derivative is also positive. First derivative could be negative too. Okay, so this is false. All right, next one. Suppose P of T models a population of dolphins 2 years after 2019. Research determines that the first derivative is greater than 0, so positive, and the second derivative is less than 0, negative. This means the population is decreasing less and less every year. So we want to figure out, is that last statement true or false? And so that's referring to the population, which is the original function P of T. Like the first derivative of P of T is telling us how fast our population of dolphins is changing. So how many dolphins are we gaining or losing per year? Then the second derivative will tell us, is that rate of dolphins, like the rate of the population of dolphins, is that increasing or decreasing? So the second derivative refers to the rate, is the rate increasing or decreasing, or the concavity of the first function, P of T. Okay, so we want to find out what is P of T doing. So if the first derivative is positive, that means that P of T is increasing. Every year we have more dolphins. It's a positive slope. So that already tells us that this is false because the population is increasing, right? It's not decreasing, it's increasing. Because P prime T is positive. That tells us we have more and more dolphins every year. So this is false. And then we also know that since the second derivative is negative, it's increasing less and less every year. So every year we have more dolphins, but just because that's in comparison to the previous year, it's actually less of a rate of change. So first year we have 10 more dolphins. Next year we have 8 more dolphins. The next year we have 3 more dolphins. The population is still increasing. We're still getting more dolphins, but we're getting fewer more dolphins. That's what it means when the second derivative is negative. All right, and then we have a question. If the first derivative is increasing, it's increasing. If the first derivative is positive, the population is increasing. if the second derivative is positive, the first derivative is increasing. So I know that's a little confusing, but if you check it out right here and here, and I'll put some plus signs, that's plus, that's negative. Okay, so when the second derivative is positive, another way of saying that is saying that the first derivative is increasing, because the second derivative gives us the rate of change of the first derivative. First derivative gives us the rate of change of the original function. Okay, so when you take the derivative, you're finding the rate of change. So the second derivative is the derivative of the first derivative. So it's also giving us the rate of the first derivative. Okay, so if that makes sense, I'll move on. Let me know if you have any questions. But number 3, if v prime t represents vehicle's velocity in miles per hour after t hours, then v double prime t represents the rate of change of velocity in miles per hour every hour at a time t. Okay, so we know that the first derivative represents the velocity. That's what they tell us. So if we're looking at the second derivative is going to give us the rate of change of the velocity. When you take a derivative, you're finding the rate of change. We're going one derivative over, and so we're finding the rate of change of whatever we took the derivative of. So that makes sense. The thing they're giving us is velocity. When we take the derivative of that, we're finding the rate of change of velocity. That is true. Okay, number 4, suppose the derivative of f of t equals that, then f of t has critical points at ... Okay, so when we're looking at critical points and inflection points, we know that critical points are when the first derivative equals 0, and inflection points are when the second derivative equals 0. So in this case, they're asking for critical points, so we want to set the first derivative function equal to 0. And that tells us our maximums, our minimums, and then that inherently is when we have a change of slope, like is it increasing or decreasing. So it's either going from increasing to decreasing or decreasing to increasing. So change in, I don't know what you call it, change in the sign of the derivative. Okay, so it's going from positive to negative or negative to positive, increasing to decreasing or decreasing to increasing. Those are your maximums and minimums, also known as your critical points. All right, so we want to find critical points. We'll set f prime t equal to 0. So we'll have 0 equals 1/3 t cubed minus 3t. And we want to solve for t. Okay, so make sure, this is really important, make sure you guys factor this first. Don't try to like move the 3t over to the left just yet. You want to factor it first because we'll find out that we have a critical point at 0, t equals 0. So first we're going to factor out a t. Okay, and then I would set t equal to 0, and I would set 1/3 t squared minus 3 equal to 0. All right, so if I just went at it straight away without factoring, I wouldn't realize that t is a 0. If you could like think about it and you're like, oh yeah, t is like, there's a 0 at 0, you're good. But like, if you're unsure, just factor it first. All right, so we know t equals 0, and then we'll also set t equal to 1/3 t squared minus 3. All right, why are we doing this? Wait, hold on. I wrote that wrong. We'll have 0 equal. Okay, why are we doing this? If either of these components, this is one component, that's another component. If either of those are equal to 0, then our entire function will be equal to 0 because anything multiplied by 0 is 0. So that's why I'm saying if t is equal to 0, that first one, then the entire thing is 0. So 0 is one of our critical points. And we're breaking it up to solve it, actually, not to check it. Yeah, we're solving it. So we're finding the zeros. We're trying to figure out at what values of t does the entire function equal 0? And then if the second component is equal to 0, then we know that the entire function is equal to 0. So I know some people were like a little confused on why I broke it up last time I did this. This is why. Okay, so I'll move the 3 over. So we'll have 3 equals 1/3 t squared. And then multiply by 3, so we have 9 equals t squared. And then remember, we have that plus and minus when we have a square root. So we'll take the square root of 9 and we'll get plus or minus 3. Okay, so we have 3 critical points: 0, -3, and +3. And that is C. Okay, so just to like reiterate my point, if we were going to solve this without factoring, I would move the 3t over to the left. And then my next logical step would be to divide by t, right? So we can isolate t. So if you're going to do this without factoring, you should recognize that when you have a t on both sides or a variable on both sides, then 0 is one of your factors. And then you would get 3 equals 1/3 t squared, and you would solve it just like right up here. So how do we get 0 again? We said that these two components in red, if either of them are equal to 0, then our entire function will be equal to 0. And we were trying to find the values of t that would make the entire function equal to 0. So when t equals 0, if this was 0 right here, this would be multiplied by that 1/3 t squared minus 3, and anything multiplied by 0 is 0. So whenever t is 0, just because that t is being multiplied by the entire function, that would make our entire function 0. So that's why t would be equal to 0. That's one of our critical points. Okay, and I'll get rid of this. All right, number 5. The derivative of L of t equals natural log 4 plus e to the power of -t is given by which of the following? Okay, so they just want us to take a derivative, but of course it's not going to be very simple. So how will we take the derivative of this? Well, you should recognize that when it looks kind of hard like this, like it looks like we've got natural log of something, but inside that something we've got like another thing we got to take a derivative of, you're probably going to end up using chain rule. Okay, and then I always forget what the chain rule is, so I rewrote it. But yeah, make sure you guys have that one memorized. So chain rule, because we've got like an inside thing and an outside thing. My outside thing is natural log of whatever, and my inside thing is whatever that whatever was. So f of x is your outside, all right? And your outside was natural log of that whatever, and we'll call that whatever x. So natural log of x. And then g of x, I'm going to put it down here. G of x is the insides. So f of x was the outsides, g of x is the insides, and that's 4 plus e to the power of -t. So we're kind of saying like g of x equals that x right here. All right, and then to use the chain rule, we're going to want to find the derivative of f of x and the derivative of g of x, and then we'll just follow it through. So we'll have derivative of f of x, and derivative of natural log of x is just 1 over x. That's a derivative rule. You should have that memorized. G prime x, take the derivative of that. Derivative of 4 is just 0. Derivative of e to the power of -t is -e to the power of -t. Yeah, and then to do that, if you guys are confused, basically, I think, I don't know, I like have it memorized somehow, but I think I just did the derivative of -t was -1, and that gets multiplied by the whole thing. E to the power of t is kind of weird. You guys probably know those rules better than I do, but okay, so we have all those all the components, and now we're going to plug them into the chain rule. And the chain rule was f prime of g of x times g prime x. All right, and so we're just going to plug it in. So we'll have, we'll start with the derivative of f of x. That's 1 over x. And instead of putting in that x, we're going to put in g of x because we have f prime of g of x. So we'll have 4 plus e to the power of negative t. And that's multiplied by the derivative of g of x. So that's negative e to the power of negative t. And that's it. We're going to see now in our answer choices what matches. We're not going to try to simplify yet because this is multiple choice. So get it to the point where it's right, doesn't have to be completely simplified, then check your answers. You don't want to do extra work and then be like, oh, I didn't have to simplify. The answers are unsimplified. Okay, so if I look here, it looks like the fourth one matches. Yes. So that is this one. Okay, so that was using the chain rule when they don't actually tell us to use the chain rule. So you have to kind of be on the lookout and recognize when you need to use it. All right, consider the plot of the second derivative provided in figure 1. The provided plot indicates that. Okay, so first thing I do when looking at graphs, make sure you recognize what is it a graph of. Like, is it f of x, f prime x, f double prime x? You need to know, otherwise it'll mess you up completely, even if your theory is all correct. Okay, so this is second derivative. Good question, why is e negative? I'm reading a question in number 5. Oh, in the work, but not in the answers. I'm not sure which negative you're referring to, Thomas. If you can clarify a little bit, and then I'll come back to it. Give me a little more detail. But back to number 6, we know what graph it is. Oh, the negative moved to the beginning. Yes, negative did move to the beginning, if that was confusing you. Yeah. So this one right here just went over here. And you can totally do that. Another way to rewrite this, if you're a little confused, is negative e to the power of negative t over 4 plus e to the power of negative t. The negative can move to the numerator, denominator. Negative kind of goes all over the place. Just make sure it's in there. All right, cool. That cleared it up. Yeah, awesome. Okay, so number 6. All right, so I would go, for this one, I would go through the answer choices and read those and then compare them to the graph. With the graph alone, you can't really figure out anything. We're just like, okay, it's a graph of the second derivative. Let's read our answer choices. All right, so first derivative has a maxima at x equals 0. All right, so first derivative graph. If the first derivative has a maxima, we can think of a maxima as a critical point, right? And we know we have a critical point when the derivative equals 0. So this is telling us that at x equals 0, the second derivative should equal 0, because that would be our critical point. Okay, so you're like, what the heck, second derivative equals 0? That's our inflection points, not critical points. Well, you have to think that our original function in this case, in this example, is actually the first derivative. So don't be like set in your ways like this is always critical point, this is always inflection point. Depends what your original function is, right? You have to think in first and second derivatives. If f prime x is our original function, then technically our first derivative in this case is f double prime x. And when your first derivative is equal to 0, you have a critical point, and that is a maxima or minima. Okay, so that's why I know that A is telling us that at x equals 0, our second derivative should equal 0. All right, so if we check it out here, we can see that at x equals 0, yes, the second derivative graph crosses the x-axis. We have an x-intercept there. That point is 0, 0. And so we know that we do have a critical point there. We don't know if it's a maximum or minimum yet, right? So it could be A or B. So those are both potential answers because yes, we do have a critical point at x equals 0. There is a maximum or minimum. But before we decide is it A or B, I want to go to C and D and tell you why those are probably wrong. So original graph has a maxima at x equals negative 0.75. Right? So if there's a maxima, it means that the first derivative of f of x, when that is set equal to 0, we would have a maximum or minimum. So this is telling us at x equals negative 0.75, f prime x equals 0. All right, and so you have to recognize that those are both critical points, but just in different scenarios. So for this one, I would think, okay, so when you have a second derivative, that's telling you that the first derivative, when that's 0, sorry, I'm like just thinking, when that's 0, you can't really tell from this graph. So this is a kind of hard one to like prove it's wrong, but maybe I would just go like the opposite of process of elimination, like find the right answer and therefore everything else is wrong. But I could think about it and come back to you guys as to like exactly why that's wrong, like how we could figure it out. But if you're taking this on negative 0.5 or negative 0.25, maybe, I'm not sure, not certain. But if you're taking this on the test, don't waste your time thinking too much. But we can come back to this one too if you guys want to talk about it. But I don't know what I'm doing anymore. So I'm just going to tell you why it's right. Okay, so we know that it's A or B, all right? There's definitely a critical point at x equals 0. And so there's either going to be a maximum or a minimum in most cases. Okay, so we want to see, is it a maximum or a minimum? And so we want to check out, is the, like, from the left of x equals 0, is that positive or negative? And to the right, is that positive or negative? And so if we're checking out the second derivative, we're thinking of the second derivative as the first derivative, right? We're thinking that the first derivative is our original function. And therefore, this graph they're giving us is kind of like our first derivative of our original function. So we can just think of it like the slope of our first derivative. So when the slope is above the x-axis, right here, it's positive, right? When it's below the x-axis, just until here, we'll like ignore this, that's negative. So if it's going from positive, then it hits that 0, and it goes to negative, that's going to be a maximum. And that is why answer A is correct. Answer A is correct. Okay. I like confused myself with the last two choices, but if you guys understand why A is correct, then I think I did it right. Okay. Let me know if you guys have questions. We'll go on to number 7. Suppose that the first derivative equals that, then f of x has a point of inflection at ... Okay, so points of inflection points, are when the second derivative equals 0. So when f double prime x equals 0. So this one isn't too bad. They already gave us the first derivative. We're going to take the derivative again to find the second derivative. Then we're going to set that equal to 0 and solve for x. Can you explain how to find the first derivative critical point from a second derivative graph? I'm sure it can be explained. Can I explain? I'll have to think about it a little. So I can come back to that at the end of class, remind me, or like the end of the session, and I will like hopefully figure it out. Okay, so we're going to take the derivative again. And we'll get 9x squared minus 3. That's just simple power rule. And then we'll set that equal to 0. Move the 3 over. Divide by 9. And then take the square root. So we'll have So minus the square root of 1/3 equals x. And then we can also distribute that square root out to the numerator and the denominator. So we can think of it as plus or minus square root of 1 over the square root of 3 equals x. And then if we simplify that, the square root of 1 is just 1. So we'll have plus or minus 1 over square root of 3. And that is D. All right, now we're going to move on to the short answer. Okay. The quantity of demand for a product at a price of P dollars is determined to be Q equals negative P squared plus 3P plus 9. Use calculus to determine the price that will provide maximum revenue. Okay, so some keywords here. They are giving us a function for, let's use like a highlighter. They're giving us a function for quantity, okay? But they want to find maximum revenue. And then our variable of interest is price. Okay, so we're probably going to have to figure out how to get that quantity function into a revenue function. This comes straight from your focus sessions. I don't know if you guys also did this in class, but definitely know this was covered on a focus session. Revenue equals price times quantity. It's probably in your best interest to memorize that. R equals P times Q. Okay. Another keyword is maximum. Maximums, when you're dealing with calculus, always think of first derivative, because when you find the first derivative, you can find critical points and you can see if there are any maximums or minimums. So maximum revenue, we're probably going to find the revenue function from this quantity function, and then we're going to probably take the derivative, find those critical points to find that maximum of the revenue. Okay, so they give us the quantity function. We want to find revenue. So we're going to do Q times P. So we'll have price times the entire quantity. Make sure you put parentheses. And that's going to give us revenue. So I'm just going to distribute that P out. So we'll have revenue equals negative P cubed plus 3P squared plus 9P. Okay, so now, like I said, we want to find maximum revenue. When we're thinking maximums or minimums, we'll probably take the derivative and find those critical points by setting it equal to 0. So let's find the derivative of revenue. Simple power rule, we'll have negative 3P squared plus 6P plus 9. Now we're going to set it equal to 0. So we'll have 0 equals negative 3P squared plus 6P plus 9. So in this case, we would probably want to factor. There are a couple of different ways to do this. First thing I would do is to factor out a 3, because you can see that 3, 6, 9 are all divisible by 3. To make it easier, I don't like having a negative in front of the like p squared or x squared. I try to avoid having a negative there. That way you can factor it nicely. So I'm going to factor out a negative 3 to get that negative out of that first space. Negative 3, that leaves us with p squared minus 2p, because we're factoring out a negative 3 from 6, and minus 3. All right, so nice. Now we have a negative 3 outside, and we can kind of just ignore it. It's like we're dividing both sides by negative 3. We'll still have 0 equals p squared minus 2p minus 3. So we want to set this equal to 0. Now here's where algebra comes in. You're going to want to factor. And so we want to find two numbers that multiply to equal negative 3 and add to equal negative 2. So that would probably be negative 3 and positive 1. We got rid of the negative 3 by dividing both sides by negative 3 to isolate the variable. And 0 divided by negative 3 is still 0. 0 divided by any number is 0. Any number divided by 0 is undefined. So 0 over negative 3 was 0. That gave us 0. So we want to see when will p minus 3 equal 0 and when will p plus 1 equal 0. Because if either of these two components equal 0, we know that the entire function will equal 0. So I want to find p minus 3 equals 0, p plus 1 equals 0. These are the roots or the zeros of the function. So p equals 3, p equals -1. I usually skip this step here. Just go to 3 and -1. All you're doing is flipping the signs. That should be mostly a review for you guys, at least the factoring. So make sure you're like brushing up on that. You never know when that comes up. Okay, so we found 3 and -1, and that's giving us a price. Obviously, we can't price products at negative numbers, so I would just like ignore this -1. Okay, really we're only focused on positive numbers. Think of our boundaries. Most we can do is give it away for free. I suppose we could pay people to take our products, but you know, like think sensibly. Okay, so our boundaries are from 0 onwards. Those are our boundaries for price. And so I'm going to do the first derivative test to find out if p equals 3 is a maximum or minimum. So remember, we're looking for maximum revenue. So 3, to use the first derivative test, I'm going to take a number from the left and a number from the right, plug them both into the derivative function, so r prime, because we're looking at is the derivative positive or negative, and then we'll find out is it a maximum or minimum. Okay, sorry. From the left, I will take a random number, let's say 0. That's really easy. Plug in 0 for r prime. So r prime 0. Let's see, if we put in a 0 here, that's all 0. Put in a 0 here, that's all 0. So we're just left with a positive 9. Remember, you really don't care what the value is. We don't really care about that 9. We just want to know, is it positive or negative? So 0, which is to the left of 3, gave us a positive derivative. Everything to the left of 3 will give us a positive derivative. Choose any number you want. Okay, to the right of 3, we can choose a number. I'd say 4, so we can have r prime 4. That's going to be -3 times 4 squared plus 6 times 4 plus 9. All right, so 4 squared is 16. -3 times 16, should probably not one. -48. 6 times 4 is 24. Plus 9. All right, so 24 plus 9 is going to give us 33. And -48 plus 33 will end up with a negative number. Again, I don't really care what the number is. Is it positive or negative? That's all I care about. Okay, so it's positive to the left, negative to the right. So it means it's going up, hits that 3 at that critical point, then it goes down. And that looks like a maximum to me. All right, so we know for sure 3 is the price that will give us maximum revenue. So $3. Final answer. Okay, so everyone understand everything about this one? It was kind of long, a lot of concepts. Understand that the reason we canceled out that -1 is because we don't really have negative dollars. We don't have negative prices, I should say. Okay. All right, I'll move on. Number 9, and then, okay, 2 pages. All right, use the provided blank plot to sketch an example of a function f of x that satisfies all of the following conditions. Okay, so I already looked through this one, and when you guys are sketching your plots, hopefully you're doing it along with me, just remember that it's probably going to be a pretty big estimation. We're all going to have slightly different graphs, but just recognize the steps that I'm taking, and as long as you follow those steps, it's okay if your graph looks a little different. We should just match in like certain components. Okay. So if we're looking at A, that gives us f of 2 equals 20. So it kind of gives us the point 2, 20. Oops, 220. Okay, that one's really easy. X equals 2, y equals 20. So we have a point right there. That's a point on f of x. Remember, we're sketching an example of the function f of x, which is the original function. Like I always say, make sure you know what graph you're looking at. Okay, next up we have the derivative. The first derivative is greater than 0, so the first derivative is positive. What does the first derivative tell us? It tells us if it's increasing or decreasing. Is the slope positive or negative? If the slope is positive, it's increasing, so it's going this way. So that's going to be the general direction of the entire function. I don't know enough to draw my function yet. I can't put anything on the graph with that information because all I know is that it goes to this green point, but if it's increasing, it could go like that, it could go like that, it could go like that. We really don't know. We just know it's going up and to the right. So we can't really draw anything yet. But we have to keep that information in our minds. It's always going up. Okay. Next up, we have the second derivative is greater than 0 for x less than 2. So to the left of that green point, our second derivative is positive. If it's positive, that tells us concavity is concave up. So concave up, like that. Likewise, d is negative, less than 0, for x greater than 2. So to the right of the green point, that's concave down. Positive, concave up, negative, concave down. That's pretty easy to remember, I think. Okay, so now we have enough to draw like a very rough sketch of what it may look like. This is where our graphs are really going to differ. But as long as it looks somewhat like this, you're cool. Okay, so it's going up, but to the left of 2, it's concave up. So I would say kind of look like that. Shoot, it's kind of concave up, right? And then I would not want to include like this piece of the concave up because that is decreasing, right? And it's telling us that our first derivative is positive. So we don't want to include this piece, which is why I started it here, and that's why I didn't do this, okay? And then for D, it's concave down past 2. So it's going to look kind of like this. Again, we're not going to include this piece. That's decreasing, and we're always increasing. All right. So as long as your graph looks somewhat like that, you're cool. If it looks like this, you're still good, okay? Just has to hit that point and look somewhat like that. All right, number 10, a business would like to manufacture open-topped rectangular boxes with a square base that have a capacity of 1,200 inches cubed. Determine the dimensions that will minimize the amount of material required to produce each box. Then it gives us phi equals LWH. Okay, so keyword here, minimize. We're thinking derivative, right? First derivative, taking critical points. And then we want to minimize the amount of material. Okay, so I'm going to define that as M because we're going to need to draw, or we're going to need to write some equations. Okay, so M is going to be the material required to produce each box, and we want to minimize M, so we're probably going to find M prime. All right, and then let's see what information we have. The capacity is 1,200 inches cubed. If you see, I drew a cube down here with a square base. That tells us that L equals W. When you have a square, all the sides are the same, right? So if this is L and this is W, L is going to be equal to W. So you could say you had 4 L's or 4 W's or 2 W's and 2 L's. But in this case, we really want to use as few variables as possible. So I'm either going to choose L or W, but I'm not going to use both. We know that the height is variable. We don't know what that is. It's not going to be the same as L or W. So I will use 2 variables, either L or W and H. Okay, and then remember this is an open box, open topped box. So we're not worried about the top. We just have the base and we have 4 sides. Another way to draw that is like this. This is our base, and then we have 1, 2, 3, 4 sides. Just like if you opened up a box. And then these sides are H, and these are W and L. And again, W is equal to L. Okay, so with that information, we can take this volume equation and simplify it. So we know L equals W, so I can choose either W or L. And then this is an open top box. They told us in the question, it's an open top box. So that's why we're not worried about the top, just the base. Okay, so volume is going to equal either L squared times H or W squared times H. You can choose one or the other. It's like saying L times H or W times H, which is going to be L squared H. You can use either. Okay. All right, so we simplified our volume equation and it's telling us the capacity is 1200. Capacity, you should think as volume. You can also take a clue from the inches cubed. When you have units cubed, that's usually volume. When it's squared, it's usually area. Okay, so 1200 equals L squared H. All right, so we have one equation. We want to find our material equation. Material is going to be that like cardboard that we're using. It's the surface area of that. So we'll have the base will be L times L, right? The area is W times L, which is in our case L times L. So base surface area is L squared. And then if we want to see the sides, so 1, 2, 3, 4 sides, it'll be 4 times L times H, right? If we're trying to find one of these sides, we have one side, our base is over here, and the base has a length of L, and our side has a height of H. Okay, so H times L, and we have 4 sides, so we're multiplying that by 4. So 4LH. Okay, so that's the surface area of the base and the surface area of the 4 sides. If we want to find the total surface area, we're going to add them. So M, which is our total material, total surface area, is going to be L squared plus 4LH. Okay, so 2 equations. This is a system of equations, and we managed to pare it down to just 2 variables. There's no point in having that W there if W equals L. You can totally write these with W's and then replace the W's with L's later, like now, but just personal preference. Okay, system of equations, let's solve it and find like an equation for M. Why do we need this system? We already have an equation for M, right? Well, it's because we have 2 variables, and we don't want to find the derivative of a function with 2 variables. We want it in terms of 1 variable. That's why we're using that volume equation and kind of combining that with our M equation to get M as a function of just 1 variable. So we can choose any variable. We can use L or H. In this case, I'm just going to solve this 1200 equals L squared H for 1 variable. So I'm going to divide both sides by L squared. So this can be rewritten as H equals 1200 over L squared. Okay, so now I can take that H and replace it in the M. So we can put this in here. We'll get M equals L squared plus 4L, and then we'll put in that H there. So 1200 over L squared. Right, so now our function is in terms of 1 variable, and we can take the derivative. First, I'm going to simplify, but then we'll take the derivative. I'm going to cancel out the L, because there's an L attached to the 4 in the numerator, and there's also 2 L's in the denominator, so I can cancel one out. So 4 times 1200 over L. It's no longer L squared, it canceled out with that L in the numerator. And then 4 times 1200 is 4800. All right, and then one last thing, if I want to use the power rule to take the derivative, I like to take any variables in the denominator and move them to the numerator. I do that by changing the sign on the exponent. So it's L to like the power of 1 in the denominator. To move it to the numerator, I'm going to take it to the power of -1. Okay, so all that was just rewriting it. Then we want to take the derivative of it next. How did I get the equation for m? Okay, so this I kind of had to come up with the question, but it told us kind of what the box would look like. Rectangular boxes, but with a square base. So that told us W and L were the same. And then I just found the surface area of those 4 pieces. So we had the base and we had the 4 sides. So I found the surface area of the base, surface area of the 4 sides, and added them. So our m equation is this and this added together. Then I wanted to get it in terms of one variable, so I combined it with the volume equation. Oh, geez. Okay. We solve for h, then L. Yeah, we solve for h, and then we're putting that into our m equation to get m in terms of just L. We also could have solved just for L and then replaced all the h's with L's, but that would have taken a little more work. So replacing the h with L's was a little more intuitive. And then we want to find the maximum, just kidding, we want to find the minimum amount of material required to produce each box. Maximums or minimums, we can use critical points. So take the derivative of m, set that equal to 0, and we'll find our critical points. All right, so derivative of m. I set it up real nice. Now we just have to use the power rule. That's 2L, and that'll be minus 4,800 to the power of L, or times L to the power of a -2. All right, so now I can set that equal to 0, and I can actually rewrite it too, and bring that L squared back into the denominator. So I only moved it into the numerator to make it easier to take the derivative of it. Now I can set that equal to 0, and then I would move that 4,800 over L squared to the right. So I'll have 2L equals negative 4,800 over L squared. And then I would multiply both sides by L squared. So we'd get 2L cubed equals, oh, and we wouldn't have a negative here anymore. Sorry. Okay, 4,800. Then we'd take, we divide both sides by 2. So we would get, L cubed equals 2,400. And then we'll cube root both sides. So we'll have L equals the cube root of 2,400. All right, if you want to do that in your calculator, which you should, you can either go math, go down to 4, hit enter, and then it'll give you like the, you guys can't see, it'll give you the cube root, and then you can type in 2,400. Or you can do 2,400 to the power of 1/3, whichever you prefer. Okay, so both will give us the same answer, 13.39. And that's in inches. Okay, so we know the length equals 13.39. We also know the width equals 13.39. Remember, width and length are the same because our base is a square, and a square has the same value for all the sides. So we know length. Last thing we should find is, yes, exactly, 2,400 to the power of 1/3 is the same thing as cube root of 2,400. I can write that here. Factor out an L and then solve for 0. If we're looking at, trying to figure out what step you're referring to, if we're looking at like this step, we can't factor out an L because one is in the numerator and one is in the denominator, because that L squared has a negative in front of it, right? So if we rewrite it, we can see that we actually can't factor out the L because they're not both in the same numerator or denominator. If we were able to factor out an L, you would have seen that when we tried to solve, we would have divided both sides by L. That's how you know. Last step for this problem is to find height, because we want to find the dimensions of the box. So that includes length and height. Okay, and width, technically. Stop. Okay. W is also that. All right, so to find h, height, we can use this equation that we came up with, 1200 over L squared, and we can just plug in that 13.39 for L. So we'll have, we'll put it here. H equals 1200 over 13.39 squared. All right, and just a pro tip, keep that number in your calculator, not the 13.39, but the 13.3888659, so that you have the most accurate answer. Don't use 13.39, use it off your calculator. So just take that second answer, take that to the squared, so to the power of 2, and then 1200 divided by second answer. And I get H is roughly 6.69 inches. Just for clarity, I'm going to rewrite this one. All right, so those are our final answers. Those are the dimensions of our box to minimize the amount of material, but have a volume of 1200. One more page, guys. Okay, Ray is taking a road trip to visit friends. Table 1 is velocity, T hours after 8 a.m., and she delivers packages north and south along the road. Okay, so this is kind of like extra information. Oop, I wanted to cross that out. Extra information. Basically, it's just telling you that she's going straight. All right, she's not like, shoo, like that would mess up her distance or whatever. Okay, but yeah, don't worry too much about the north thing. In calculus, it's really common to be like, oh, we're gonna go north for this many, and then east for this many, and then south. So yeah, don't let that trip you up. Okay, so we don't really care about north and south. We're just going straight. And assume her velocity is strictly increasing or decreasing between data points. Okay, so if it's like following a trend between data points, this is just telling us that it's not gonna like curve on us randomly in between data points, right? Not super important, but cool. Just another assumption. Okay, is the acceleration positive or negative from over the interval 1.5 to 2? So the interval in question is right here. These 2 points. Is the acceleration positive or negative? Okay, so let's go back to some of my notes. When we're looking at a position function, f of x is the original function. That gives us position, distance traveled. Okay, this is like basic, very, very basics of physics, calc-based physics, okay? Original function gives us position. The first derivative function gives us velocity. How fast are we moving in that position? How many feet am I traveling per minute? Okay, units can vary, but velocity is how far we're going in a unit of time. We're assuming x is time. Okay, and this is like in the orange, that's not applicable to every problem. Like I said, it's like very basic physics. Only applies to a certain number of problems. But for me, at least, I feel like it helps me kind of conceptualize the derivatives. Okay, and then the second derivative is acceleration. How fast is our velocity changing? Like you're driving a car, right? Assume the forward direction is the positive direction. Our velocity is positive. I'm driving down the street. If I'm accelerating, my second derivative is positive. So I'm turning out of my driveway, I step on the gas, and I'm going faster and faster and faster. My velocity always remains positive. I'm always going forward, and my acceleration is also positive because I'm getting faster and faster. If I were looking at a second derivative that is negative, so I'm deaccelerating, my acceleration is negative, my velocity is still positive. I'm still going forward. I'm not going backwards. Then my velocity would be negative. So my velocity is positive. I'm going forwards. My acceleration is negative when I'm deaccelerating. So I'm stepping on the gas. So I'm still going forward, but less and less as I approach the stop sign. Okay, so acceleration positive, we're getting faster and faster. We're always getting a little bit faster, like we're always going forward, but we're increasing the rate at which we're going forward. When acceleration is negative, we're decreasing the rate at which we're going forward. Right? Hopefully that maybe cleared it up, kind of, but that's the context we're thinking of it in this problem. Okay, so is the acceleration positive or negative over the interval 1.5 to 2? All right, so now this is a little confusing because they're telling you that f of t is velocity. Normally we're thinking of the first derivative as being velocity, but in this case, they're telling us the original function is velocity. That means that if the original function is velocity, then acceleration will be given by the derivative of velocity. So it's no longer going to be the second derivative, it's going to be the first derivative. So remember, everything is in relation to what they define as being the original function. Okay, so over the interval 1.5 to 2, our velocity is going from -30 to -15. Okay, so remember what I was saying. When velocity is positive, we're going forward. When velocity is negative, we're going backwards. So in this case, it's kind of like she's going backwards at a speed of 30, but then she's slowing down. Now she's only going backwards at a speed of 15 miles per hour. I don't know what she's doing, but anyways, just ignore the practical side of it. She's going backwards down the freeway really, really fast at 30 miles per hour, or semi-fast, not fast. But then she gets like really slow. Now she's at 15 miles per hour, but she's still going backwards. Is she accelerating or deaccelerating? Think about it. Let me know. Put it in the chat. What do you guys think? Accelerating or deaccelerating from 1.5 to 2 if her velocity is slowing down? All right, I have one answer. Someone says deaccelerating, deaccelerating. Okay, so this one is like super confusing. So this is kind of where our like brain tells us one thing and you're like, yeah, that's right. But then you do the math and you're like, okay, hang on a second. Okay, so yeah, let me explain it. So most of you are actually wrong, but very good try. That's definitely what I would have put. But when we do the math, we'll see why that's wrong. Okay, so we are getting, let's see if I can explain this. We are getting slower, right? Technically, if we're talking about speed, do you guys know the difference between velocity and speed? Sorry, I'm like kind of going off on a tangent, but this is important. You'll actually use this later. Velocity has direction. Speed does not. So if we're looking simply at speed, yes, she is getting slower. She's going from 30 miles per hour to 15. But velocity has direction. Velocity has positive and negative. That tells us, are we going forward or backwards? Speed doesn't care which way we're going. But we're only like talking about velocity here. So if we're going from -30 to -15, we're actually increasing our velocity because we're starting to go forward. -15 is higher than -30. So even though we're going slower, our velocity is increasing. And when our velocity is increasing, when our derivative is increasing, our second derivative, or in this case, when our original function is increasing, our derivative of that, our acceleration, is positive. Okay, so mathematically, if that didn't really make sense to you, don't worry. We want to find the rate of change between 1.5 to 2. Right? Rate of change gives us a derivative. The derivative of velocity is acceleration, which is what we're trying to find. So let's find the rate of change between 1.5 and 2. Do you guys remember how to do that? Rise over run, y1 minus y2 over x1 minus x2. So we'll have y1 minus y2 over x1 minus x2, or y2 minus y1 over x2 minus x1. Doesn't matter, same answer either way. So we'll put in y1 as negative 15, y2 as negative 30, x1 as 2, x2 as 1.5. And so that will be negative 15 plus 30 over 0.5. That's 15 over 0.5. And that's 30. I should know that. Okay. All right, so 30 is the rate of change between 1.5 and 2. We're not really worried about what the number is. In this case, we're just worried, is it positive or negative? We got a positive answer. Our acceleration is given by the rate of change of the velocity. Our acceleration was positive over the interval. Why? Because our velocity, even though we were getting slower, it was going more and more in the positive direction. So our velocity was increasing. When something's increasing, it means that the derivative of that is positive. Derivative of velocity is acceleration. Okay, so I said the same thing like 1,000 times. Hopefully one of them stuck. Why does velocity have direction? Shouldn't now make a difference what direction you're going in? I guess I don't have a good answer to that. It's just like an inherent thing. Velocity has direction because it just tells us, are we going forward or backwards? And that's important information, especially in physics. You need to know, are you throwing a ball in the upwards direction or the downwards direction? Because that'll tell you where it'll be at time t. So that's why we have speed and we have velocity, because we need those two different things. Sometimes it doesn't make a difference what direction you're going. So then you use speed. When you use velocity, you need to know the direction. Okay. So as long as we're cool on that, let me know if you guys have any more questions though. But we'll move on to 12. Okay, determine the derivative of this. You do not need to simplify. Okay, this is such a gross derivative. I'm sorry, guys, in advance. But like I said earlier, this session, if we're like, oh, this is like really complicated, it looks like we have like a derivative within a derivative, we can think of chain rule. We'll find out that that's not the only rule we'll have to use. Let's start with that one. Okay, and then to simplify it, I'm actually going to ignore the second part for now. And we'll do it a little bit later. Okay, we're just going to leave it for later. Just going to tackle the beast first. Okay, so think of inside and outside, right? Outside is going to be f of x, inside is g of x. So outside is f of x. And so that would be x to the power of 179. We're going to leave that inside stuff for g of x. So x to the power of 179. And to replace that x, we have g of x, which is the inside stuff. And that's x squared plus 4 over x cubed minus 8x. All right, so we defined our components of the chain rule, and now we're going to find the derivative of f of x and the derivative of g of x so we can use the chain rule. And we'll just plug it in and we'll be all good. That's the idea, but if we find the derivative of f of x, that's nice and easy. Power rule, we have 179, x to the power of 178. But when we go to find the derivative of g of x, we're like, oh shoot, that's kind of a hard derivative. We can't just do that using the power rule. We're going to need the quotient rule. Okay, so to find g prime x, we're going to use the quotient rule. I'm going to change colors. This gets a little confusing, so just really focus, bear with me here. So quotient rule, again, we want to define f of x and g of x. Okay, so just to clarify, chain rule is, we're using the chain rule because we have a derivative where we have like a derivative inside of a derivative. So that's why we're using the chain rule. We're using the quotient rule to find the derivative of g of x because we have one thing divided by another thing. So we're using the quotient rule to find the derivative of g of x. Okay, and then the quotient rule, I I just want to make sure I get it right. Quotient rule is, okay, cool. I think I got it. So we want to define f of x and g of x. You can use any variable. Sometimes I use a and b, but I feel like that might have confused you guys more last time I did that, so I'm just going to stick with f of x and g of x. But f of x is the top and g of x is the bottom. So f of x is going to be x squared plus 4. Remember, we're only dealing with this g of x right here. We're just trying to find the derivative of this g of x so we can apply it to the chain rule. So in this case, our bottom is x cubed minus 8x. Okay, then to use the quotient rule, we're going to find the derivative of f of x and g of x, the ones in red. And this is pretty easy. That's 2x. Derivative of g of x is 3x squared. Okay, so now we have our components defined for the quotient rule. We're going to use the quotient rule to find the derivative of g of x in black. Okay, so we have, for the quotient rule, it's f minus g prime f, and that's divided by, oh, my bad, thanks guys, minus 8. Good catch. Thank you. How did I get the derivatives? I just took the derivative of f of x and g of x. So I know the top was f of x, bottom was g of x, and then I found the derivatives using the power rule. So x squared, derivative of that is 2x. Derivative of 4 is 0. Derivative of x cubed is 3x squared. Derivative of negative 8x is negative 8. Thank you for that, guys. Okay, so I wrote out the quotient rule, and then I think I missed something. G squared. Yeah. Okay, now I'm just going to plug that red stuff into the quotient rule, and I should come out with g prime x in black. Okay, so f prime x is 2x multiplied by g, that's x cubed minus 8x, minus g prime x, so that's 3x squared minus 8, and multiplied by f, that's x squared plus 4. And that is all over g squared, which is x cubed minus 8x parentheses squared. All right, all of that is equivalent to g prime x, the black one, okay? So I don't even want to rewrite it, okay? So yeah, this one is also right there. Okay, so now we have our components for the chain rule. We're going to plug them into the chain rule. Okay, so remember the chain rule was f prime of g of x times g prime x. Okay, so that's our rule for the chain rule, and we're just going to wrap it up, put it in there, and we're almost done. Okay, so f prime was 179x to the power of 178. So we'll put in here 179 x to the power of 178. Instead of putting in x, we're going to put in g of x because we have f prime of g of x in the chain rule. So we're going to put in x squared plus 4 over x cubed minus 8x. And then that's to the power of 178. All right, so that was f prime of g of x. Now we're going to multiply by g prime x. And so that was that huge thing we found with the quotient rule. I am just going to copy that because I'm a little lazy. All right, and so that is almost all of our answer. We're very, very close. But if you guys remember, we did omit that green part, the 3 times the 6th root of x for simplicity. So we just got to make sure we throw that back in there. And when we take the derivative of that, I guess I'll use orange. Okay. I just want to take the derivative of that real quick and then add that on to my final answer. And so I would rewrite this. So I would have 3 times x to the power of 1/6. It's really hard with those squares and like the roots and stuff to take the derivative. It's much easier to put it into fraction exponent form because then you can use the power rule. And so power rule, we would multiply 3 by 1/6 So we would get 3 6 times x to the power of negative 5 6. 1 6 minus 1. And then we can simplify that 3 6 to 1 half. Okay, so our final answer is this. Let's see if it'll let me make it small. Okay, cool. And then plus 1 half x to the power of negative 5 6. Okay, and that is our final answer. I promise. Okay, and then I'm just gonna double check that. Okay, looks good. All right, I'll scroll up. So let me know if you guys have any questions. I can go back and answer some that I skipped over. Oh, okay. Maggie's question from like around 6:30. I can answer that. I remember now. So if you guys are not done with this one, make sure you take a screenshot real quick, and then I'll move on. Let me know if you guys have any other questions. We can go over those too if you guys have anything you want to talk about, but basically done with practice test 2. So okay, I'm gonna move on in 5, 4, 3, 2, 1. Yeah, you're welcome. Okay, C and D with number 9. I will come back to that one. Let me answer this one question. Okay, and then I'll go to number 9. All right, so the question was, how do you find the critical points for the first derivative from the graph of the second derivative? And so I think we had a second derivative graph somewhere. Not this one. This one. Okay. Well, all right, I'm just going to erase some of this stuff. All right, so we have a second derivative graph, and we want to find the critical points of the first derivative. So we want to go back one step. And the opposite of a derivative is an integral, BT dubs. I don't know if you guys learned that in this class. You might, but you haven't yet. But anyways, if we're going back from the second derivative to the first derivative, it's like we're taking an integral, the opposite of a derivative. Okay, so when we have a critical point of the first derivative, that's telling us that we have a minimum or maximum. Okay, and so when our minimum or maximums are there, that's when our derivative of whatever that graph is, whenever that derivative equals 0, we have a critical point. Okay, so when we have our original graph being f of x, we took the derivative to find f double prime x, f prime x, took the derivative to find f double prime x. We only took one derivative, right? And when we take one derivative, it's like our first derivative, don't let this trip you up. When we take one derivative to get to f double prime x, we're taking the first derivative. When that first derivative equals 0, that tells us that our original function had critical points. And in this case, we're thinking of f single prime x as our original function. So wherever f double prime x equals 0, we have critical points there. That's where we have minimums and maximums for a graph of the first derivative. Yeah, you're welcome. So in this case, looks like wherever it crosses the x-axis is where we would have critical points for the function previous to this. Okay, so not necessarily the original function, like f of x, but since this is the second derivative graph, we can find the critical points for the first derivative graph. So there, and right there. Does that answer your question with that one?
Okay.
Let me know if you have any.
About the graph.
Yeah.
So like if one of the options was we have a so you know how we had a minimum at 0? If one of the options was that we had a minimum at like 0.75, would that be considered what, like the 0? Because it's below the axis and then above, so that would be a minimum, right?
I'm not sure I followed all of that. If we had, so you're like referring to answer choice B, the minimum at x equals 0, and
No,
then
no,
you,
I'm just saying, like, if one of the options was we have x equals 0.75, and then we would have a point there, like right here. Oh, okay, that's 0.75. I meant where it crosses the x-axis, like right there.
oh, like negative 0.75 or
On the other side.
other side. Wait, I'm a little lost. Oh, like right here or?
Yeah, like right there, right before 1,
Okay.
where it crosses the x-axis.
Oh, right here. Okay. I think I got it now. Okay. Sorry. Okay. Got the point.
Would that also be considered a point if it was an
Um,
option?
yes, because this would be negative and this would be positive. So, well, yeah, minimum. Oop.
Okay. Because I was just confused on that.
Yep. Spot on. And then why wouldn't those points be the critical points of f double prime x? Okay, so the critical points of f double prime x are the maximums and minimums, right? So that would be here, here, here. Okay, so if you want to find critical points, if we're looking at the graph we want to find the critical points of, that will be our maximums and minimums. If we want to find the critical points of the derivative graph, so say we wanted to look at the triple derivative graph, on that graph we could find where it crosses the x-axis, where does it equal 0, and that would also give us critical points. Yay, I'm glad you got it. Awesome. Okay, so good, if that makes sense. Awesome. I'm going to go back to number 9, and then I'll go over this one. Oh, yeah, it's a hard one. Okay. C and D with number 9. Number 9. C and D. Okay, yeah, for sure. This one's a little confusing. So we know that when the second derivative is positive, it's concave up, right? That's like something you should just know. Just like how you know when the first derivative is positive, the graph is increasing. So when the second derivative is positive, the original graph, f of x, is concave up. When the second derivative is negative, the original graph of f of x is concave down. And so in this case, I had to make sure that everything to the left of 2, that point 220, was concave up, so like following this trend. And then everything to the right of 2 was concave down, following this kind of trend. Just like I drew those kind of parabolas here, I think of them like parabolas. Concave up and concave down. Up and down. All right, and then the reason I drew it like that is because we wanted to make sure that we want everything to be increasing at all times. And if we look at this concave up and concave down, we can see that this half of the concave up and this half of the concave down, they actually have negative slopes, right? They're decreasing. And we can't have that for this problem because B told us that everything is increasing. The first derivative is positive, so it always needs to be going in this direction. It can't be going in this direction, which is why I didn't include that part of the concave up and the concave down. So it's not positive or negative, it's a concave up or down, where 2 is the max or min of that side. I think you're really close. 2 is not necessarily the max or min. 2 is the inflection point. That's actually a really good reminder. This is an inflection point. 2 is where it's changing from concave up to concave down. Is there any way I can explain how all the graphs relate based on sign increasing, decreasing, concave up, concave down? I can definitely try. That would be very helpful to you guys, I think. Let me go back and answer the previous question, and then I will give that a shot, Maggie. The question I'm going over is, can we go over an example where we are given the second derivative and we're asked to find the original function? Okay, so that is truly an integral. And you guys haven't learned enough to like do it like properly. But if we're given the second derivative and we want to find the original function, best way to do that is just work backwards. Correct me if I'm wrong, but I'm pretty sure your guys' exams are mostly multiple choice, if not completely. So if they give you a question like this, and they give you an equation like 3x squared, and they're like, find f of x, we'll say 3x squared plus 6, then f of x will be your answer choices. So it'll be like A is f of x equals dot, 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 B f of x equals dot, 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 and on and on. So they'll give you f of x's. Since you guys only know derivatives and you don't know integrals, start with the answer choices, take the derivative twice, and then see what you come up with. If you come up with 3x squared plus 6, that's the right answer choice. If you come up with anything else, that's the wrong answer choice. Does that make sense? That's how I would approach those problems. Do it like that. Cool. So basically, when you do it like that, it's just a simple derivative. Just take the derivative twice. Okay, so next question was, is there a way to easily find the second derivative? No, you just got to take the derivative twice. Yeah, there's no shortcut. Not that I know of, at least. Explain how all the graphs relate based on sign. Okay, so this one's, I don't even know how I'd like approach this from Maggie's question, but I guess we can just take like an example graph of f of x. And then we can, we'll just draw something here. All right, so if this is a graph of f of x, imagine it's a really nice graph. There are like a few things we can, like key points to consider that show up very often in this class. One is maximums and minimums. Okay, so those are in green. Maximums slash minimums. Those are given by critical points. How do you find critical points? You can check out the first derivative and set that equal to 0. So when f prime x equals 0. And that will give you those maximums and minimums. If you want to classify them, you're taking the critical points and saying, are they maximums or minimums? That's called classifying. You'll use the first derivative test, which is that number line, and you put the critical point here, and then you find is it positive or negative, and you can see is it a maximum or minimum. So that's what the first derivative is commonly used for: critical points, maximums, and minimums. The other main point is inflection points. Inflection points have to do with concavity. So when you have a change in concavity, you have inflection points. That's when the second derivative equals 0. Where are those at? Okay, so we know concave up looks like this. Concave down looks like this. When they meet, that point where they meet, right here, that's an inflection point. So this isn't maybe something you really need to know, but it's like an important concept. You know, why not know more information? At your inflection point, your tangent isn't a straight line, but the graph is at a straight line, very close. You want to see where the graph is like almost linear. So if we were to draw a point alongside the graph, it would be linear. That will be your inflection point. You can really only estimate off the graphs, but there's a reason for this. Okay, so I'm saying my inflection point is probably right there, right there. This one isn't really well drawn, but like right here, and maybe right here. Where that graph is going, like if we have it going from concave up to concave down, where is the graph almost like linear? That point is always your inflection point. Why is that? When we have a linear graph, the slope is constant. The second derivative is checking out is telling us how fast the rate of change is changing, right? So it's telling us what is the rate of change of the slope. Okay, so just follow me here. Inflection points are given by when the second derivative equals 0. When the second derivative is equaling 0, that's telling us that the slope is not changing. The slope is constant when the second derivative equals 0. If the slope is constant, we have a straight line. That's why your inflection points are when the graph is a straight line. Okay, so it's all connected if you can just make those connections. I don't think that's necessarily required for this class, but like it's a really great concept to know. Okay, so blue is giving us inflection points, change in concavity, usually at a straight line. If you're confused by this, like don't worry about it. Don't let it confuse you more, but it's a good thing to know. Okay, so do you guys have any other concepts you want to go over with this graph? I'm not sure what else to go over with this, but let me know if you guys have any like specific questions. I can keep going. Yeah, have a good night. Oh, okay, here's one. We want to see where is it positive and negative. So where is the first derivative positive and negative, and where is the second derivative positive and negative? That's important. So when the first derivative is positive, that means that the graph is increasing. So that's like right here to here. That's from critical point to critical point. So it's increasing from one critical point, assuming we have like one right down here. And then from the next to next, we'll have decreasing, right? So here we have it increasing, here we have it decreasing. I don't think I'm gonna leave that in there, but basically increasing slash decreasing is from critical point to critical point, from CP to CP. At the critical points, our slope is 0. Everything in between those critical points needs to either have a positive slope or negative slope. There are no other options. You have 3 options: positive, 0, or negative. If it's not a critical point, it either has a slope of negative or positive. If it's negative, it's decreasing. If it's positive, it's increasing. Okay, so concave up and concave down is from inflection point to inflection point. See the relation? So concave up, slash concave down is from inflection points to inflection, can't spell, inflection points. Okay. So likewise in this blue, it's concave down from this point to that point. It's concave up from this point to that point. Concave down from this point to that point. Concave up is positive, concave down is negative. All right, how do you guys feel about that? Pretty good, hopefully. How would you graph f prime x if this graph is given as f of x? Okay, so if we're trying to graph the derivative of this graph, this is kind of hard on my like makeshift graph, but we'll want to see where our critical points are. I think that's one of like the most important things to do when trying to graph the derivative graph from an original graph. So we're looking at, so we have the original graph already drawn, and we're looking at the first derivative. I'll see where are my critical points. So let's assume that this is at x equals 3. This is at x equals 4, 5. Okay. All right, so that's given by our critical points. So we have a critical point at x equals 3, x equals 4, x equals 5. And then for the fun of it, let's say we have one at x equals 0. We don't really quite, but you know, we'll pretend, okay? X equals 0. So that means that x equals 0, 3, 4, 5 critical points. Critical points tell us that the first derivative is equal to 0. Okay, so we already have 4 points on our derivative graph. Whenever x equals 0, 3, 4, 5, y equals 0. The y-axis on our derivative graph is giving us slope. Slope at our critical points is 0. Okay, so we'll have a point at 0, 0. And then 1, 2, 3, oh shoot. 1, 2, 3, 4, 5. Okay. Another point at 3, 0. Another point at 4, 0. And another point at 5, 0. Okay, so those are the 4 points at which our graph is going to cross the x-axis, because those are the 4 points where we have critical points where the first derivative is equal to 0, the slope is equal to 0. Okay, so in between those 4 points, we're going to fluctuate from positive to negative. So to the left of that 0 point, I'm looking at this one right here, we want to see, is that negative or positive in terms of the slope? Is it decreasing or increasing? It's going this way, right? So it's decreasing. Decreasing is a negative slope, a negative first derivative. So it's going to be below the x-axis. I'm totally like not making this very accurate, but it's going to be somewhere below the x-axis. So it's going to go up to that green point. All right, and then from 0 to 3, is it increasing or decreasing? So from, oh gosh, from here to here, is it increasing or decreasing? It's increasing. The slope is positive. Slope is going to be above the x-axis. So we might have a slope that, and this can actually get really complicated, so I don't want to mess with you guys too much, but okay, it's going to be above the x-axis. All right, now we can kind of speed up. From 3 to 4, it's decreasing. It's going to be below the x-axis. From 4 to 5, it's increasing, so above the x-axis. And from 5 onwards, it's decreasing, so it's going to be somewhere below the x-axis. I can't tell you exactly what it's doing in between those critical points, but I know for sure it's above the axis or below the axis, and it's hitting at those points. Yeah, no problem. I'm going to add one quick letter, or one quick layer of complexity, because why not, guys? We can also check out our inflection points on this graph, right? So if you think about second derivative is the derivative of the first derivative. So the second derivative's inflection points are the first derivative's critical points, right? So the inflection points in blue on our original graph are actually giving us the minimums and maximums of this derivative graph. So imagine that this blue point is falling at x equals 1. That means right here we have a maximum. All right, and then we have another blue point here. We have a minimum here. Another blue point between 4 and 5. Got a maximum here. And then we'd probably have like a minimum down here. Okay, so that kind of like tied a lot of stuff together. Probably more detail than you'll end up using, but I don't know, maybe not. So you guys will have to let me know if you use any of this on the test. So yeah, hopefully that helped. You guys have anything else for me? I'll stick around for another like a few minutes, so take your time.